Hey everybody, welcome back. We're going to be talking more about policy gradient methods today and then starting to talk about imitation learning, but we'll do a quick refresh your understanding to start. I think everyone agrees that it will not necessarily converge to a global optima, so that's great. There's some differing opinions about some of the other ones. So maybe turn to a neighbor and talk about whether a baseline term can help to reduce the variance and whether or not after one step of policy gradient, the resulting policy can get worse.
My socket seems to be like bit high. Yeah, because that's not 4.2.
Okay, great. All right, so I think a lot of people remembered from last time that in general, a baseline term does help with the variance, and that's one of the reasons we are adding it. You can initialize it with a you can't initialize it with a deterministic policy. Does somebody want to say why? What's the problem with deterministic policies? Yes, and remember your name.
Potentially there's like an action that the policy will never take, so it's not able to reach a local minima or optima.
Right, yeah, so if you're exactly said, so if you are only taking actions deterministically, you're never going to know about what other actions are in that state. So if your current policy is suboptimal, you won't get to the optimal state. And then the last one is something we're going to talk more about today. So in general, it can get worse. This is true. In general, we're not guaranteed to have monotonic improvement. We would like to have monotonic improvement, but in general, policy gradient doesn't guarantee that. But last term with PPO, we saw things that are trying to get more towards that kind of monotonic improvement. Okay, great. So what we're going to be doing today is we're going to talk a little bit more about PPO and some of the sort of theoretical underpinnings of it, as well as another feature about it that we didn't talk about last time. And then we're going to start talking about imitation learning. Okay, so first, and all of you guys are going to be implementing PPO as part of your homework, as well as reinforce, so you'll get a chance to practice with this. We're first going to talk about generalized advantage estimation. So first, let's just refresh our memory of some of the challenges with policy gradients that motivated PPO and a whole bunch of other research on sort of better policy gradient methods beyond reinforce. So in general, we're using theta to parameterize the policy space, and we're just going to do stochastic gradient descent to try to get to a good value, a policy with a good value. The challenge is that in general, when we did reinforce, the sample efficiency was poor. We had to get data from one policy, take a single gradient step, and then get more data from the new policy. And as we were just discussing, I think I was mentioning this, or maybe, that the distance in the parameter space is generally not equal to the distance in the action space, so sort of the policy space. So when you make a small change in the parameters, it might really change the type of actions you take. So in proximal policy optimization, we saw two different ways to try to make it so that we could essentially take bigger steps in between each run of when we execute a policy, but do so in a way that would try to encourage monotonic improvement. And so we saw this bound, and we're going to come back to that very shortly, which looked at sort of how we could try to approximate the performance of a new policy under only using the data that we have right now. So that's an instance of sort of off-policy estimation. And the bound showed that this relates to the KL divergence between the actual actions taken under the new policy versus the old policy. And in PPO, that you could either do so this adaptive KL penalty, which sort of says don't go too far from your previous policy in terms of the actual actions it takes, or a clipped objective, which is going to do something similar. Right, so one thing that you probably noticed, and particularly if you started implementing this already, is that we talked last time a lot about using the advantage function. So we talked about how we were going to be doing, and in general, for sort of policy gradient, we're often going to want an advantage function. And you might wonder what we're going to plug in for that. There are a lot of different choices for what the advantage function could be. So what we're going to talk about today is a particular choice that was used in PPO, and that can be pretty powerful. So let's go back to last lecture before we introduce PPO and talk about the end-step estimators. So in general in class, sort of probably since the second lecture or so, we've been talking, second or third, I guess, probably third, lecture 3. We were talking about this trade-off between methods that bootstrap and use the Markov property, such as temporal difference learning, and methods that don't leverage anything about the Markov property, like Monte Carlo. So in particular, we've talked about cases where this is sort of a temporal difference estimate, where you just have the immediate reward plus gamma times you immediately bootstrap, you plug in your estimate of the value of the next state, versus ones like A infinity here, where basically we have a Monte Carlo estimate. Obviously, you can't actually go out to infinity. You'd have to have like episodic cases, but we generally have been focusing on episodic cases so far in the class, minus the value. So the blue there is just us subtracting off our current value, so we have this advantage estimate. So we talked before about sort of the trade-offs between these different estimates and how some of them would have higher bias and some of them would have higher variance. And what I'm going to talk about now is sort of a way to use these to try to get to a new form of advantage estimation. And it also involves a technique that comes up a lot in reinforcement learning, so it's a useful thing to be aware of. So what we're going to do is we're going to define something called delta VT. Let me just highlight this. And what this is it's just essentially here, the TD backup. So this is just what we've often seen, where we have our immediate reward plus gamma times V of the next state. So notice here that we've got a time step T. So that's going to be important. And then this is just the value, our current estimate of the value of the state. So this should look like normal. This is sort of the same advantage as up here. Okay. But note, I could plug in different T's here. Okay, so we've defined this new thing called delta. So when we use this new delta, then we would say that our advantage with the advantage function we've seen before, where we use a TD estimate, is just exactly equal to delta VT. Why is it V? Well, V is specifying here what value function we're going to plug in. And this is just exactly equal to this. So same as what we saw before. Now the next thing that we can say is, well, actually, what is the advantage for if we use this two-step estimate? That is this. Okay, so we've got this expression. And that is exactly equal to delta VT plus delta VT plus 1. So I'm just going to write that out so we can see it for 1 second for why that's true. Okay, so we had RT plus gamma V of ST plus 1 minus V of ST, that's this term, plus gamma R of T plus 1, because notice here, this is T plus 1, okay, plus gamma V of ST plus 2 minus V of ST plus 1. Okay. So when we do this in this way, what we'll end up canceling here is the V of ST plus 1. So note we have a gamma here in the front. So we have this term cancels with this term. Oops, sorry. This term cancels with this term. Let me just be a little careful here. We're going to have this term cancels with this term. Good. We're going to get the two rewards, RT and RT plus 1. The second one, so that's here and here. And then we have gamma squared times V of ST plus 2. Okay, so I just wrote out exactly what the definition was of delta and delta T plus 1. And essentially the important thing to see here is that one of the terms canceled. Okay, and so that's why we ended up getting exactly the same expression for A2 as we had before. And you can repeat this. And what will happen is kind of all of those intermediate terms, these things where you were bootstrapping, will cancel along the way. So this is why it's called a telescoping sum, because here we're adding something that at the next round we're going to subtract from the next one, and so those are going to cancel, and so you just end up getting all the discounted sum of rewards plus the last term. Who's seen telescoping sums before? Okay, so maybe about half the people here, okay? So for something this is really familiar, for something this might be new, it's a useful technique to know about because it comes up in a lot of the reinforcement learning proofs. Yeah?
Can I ask, just in comparing this to the equation for A hat sub T2 above,
yeah.
Are we basically saying that gamma squared V ST plus 2 is equal to gamma V ST plus 1?
No, we're just actually literally canceling it. Good question. So when we write out this expression, there's a gamma in front. And because there's a T plus 1 here, this will become S of T plus 2. This will become S of T plus 1, and there's a gamma. So this will be a gamma times a minus V of ST plus 1, and that will cancel with the V of ST plus 1 in the previous one.
Okay, got it.
Yeah.
So
Yeah.
A hat to T, like on top and the one on the bottom, are they equivalent then?
They're identical.
Identical, okay.
Yeah. Yeah. That was a good question. So yeah, I've written this in this notation now with the like delta notation, but this is exactly equal to this, which is the same. So these are identical. Ooh, yeah, so thanks. So there's a typo there. That might be the question. Yeah. Let me just highlight that. So this should be T. Yeah. In general, we're always bootstrapping with the final time step. Thanks for catching that. Yeah, so these all end up being exactly equivalent, and we've just rewritten it in terms of this delta notation using a telescoping sum. Okay, so these are just different n-step estimators. We haven't done anything new yet in terms of, we've rewritten things, but we haven't introduced any new type of estimator. These are just different advantage functions, and as you might imagine, the first one is going to be low variance, high bias. The last one is going to be low bias, high variance. So generalized advantage estimation involves taking a weighted combination of k-step estimators. Okay, so we had here, this was just lots of different estimators, and you might say, well, how do I pick among them? I'm not sure I'm going to pick among them. I'm just going to take a weighted combination of all of them. And in particular, you could just take an average weighted combination. So let's just step through this a little bit just to see how we do this. So what this is saying here is I'm going to take the one-step estimate advantage estimator plus lambda, I've introduced a new parameter here, lambda, times the 2-step one, times lambda squared plus the 3-step one. I'm just saying like, okay, well, why don't I use all of my estimators? And I'm going to weigh my different estimators. Okay. So now what I'm gonna do is I've next just written this in the sort of the delta notation that we saw on the previous slide. Okay, and now what I'm gonna see is that some of these terms appear a lot of times. So there's this term appears in all of the terms, in all of the advantages. The second one only appears in the second to the last one, etc. So I'm going to collect terms. Okay. So I'm going to write this as follows. And this was introduced in a previous paper to PPO, and then PPO builds on it. Okay, and just notice what I've done there. I've noticed that I had this term. So I'm just taking all of those terms and I'm noticing how many lambdas I had in front of them. Okay. And then I'm going to have delta t plus 1 b times lambda times 1 plus squared, or I'll write it differently. So this term is going to start with lambda plus lambda squared, because it's in the second through all the rest of the terms, plus all right, so I'm just rearranging the sums. And now when I look at this, I realize that I've got a geometric series. Okay. So this is just going to be equal to 1 minus lambda times lambda tv divided by 1 minus lambda plus, let me just make sure I've got, I'll put it on the next page just to make sure there should have been a gamma here. Let me just put a gamma. I'll write it out cleanly in the next slide so this will be clear. Okay, so we also had a gamma here from before. Okay, so gamma squared. And then what you do is you realize this is a geometric series that goes to 1 over 1 minus lambda. And then this is gamma times lambda, 1 over 1 minus lambda. And this is gamma squared times lambda squared. I'm just using the fact that this is a geometric series. It's fine if you haven't seen this. If you've done real analysis, you've seen this before. And that means that the term below just looks like the following. And this was introduced by a previous paper. And the idea there was to say, well, why don't we just take a kind of a weighted average over all these different terms that have different biases and variances, and then we can re-express it compactly. We don't actually have to compute all of the advantages separately and track them. We just are going to keep track of these deltas. And these deltas are pretty easy to keep track of because those are just like these one-step differences between, so just remind ourselves what the deltas look like. The deltas are pretty easy to keep track of because they're just the difference between your previous estimate and your new reward plus gamma v of st plus 1. So you can kind of just keep track of those over time. And then you're just weighing them. Okay, and our derivation just followed. And so then you just sum these up and you essentially have different weights. Okay. All right, so let's think about what this means in terms of bias and variance, as we often like to, in terms of the estimators we're using. So this is trying to be an estimate of the advantage, and we'll do a check your understanding now about how different choices, so this is a discount factor, so this is the discount factor, comma, your choice of lambda, which is how much you're weighting earlier ones versus later ones. So GAE is generally a function of these two hyperparameters. And let's think for a second about what this does for bias and variance and how it relates to TD. Can you select multiple or no? You can, okay, good. I see, otherwise the TA that's helping make these, I can just check with them. And feel free to go to the previous slide to look at the definitions. And the reason these all are really important is because if you get better estimates of the advantage, you're going to get better estimates of the gradient. If you get better estimates of the gradient, you can hopefully use less data to get to that really good policy. And so that's why people spent quite a lot of effort thinking about, with sort of using deep neural networks, both either for the advantage or for the policy, how can we really quickly get good estimates?
Is gaze like comma zero even defined? There's a 0 to 0.
There's a zero. Is
In the
this
first-
defined?
Yeah, because in the first term there will be 0 to 0 flux.
0 to the 0. It shouldn't be to the x, but oh, you mean here? You, in that case, you would just plug 0 in up here. Okay, and then that would disappear and you would just get this. All right, why don't you turn to your neighbor and see if you got the same answer. I think you can use the definition of 0 to 0 is fine. Yeah, it's easier to look at the
Would you not look at the secondary body when you first line?
It's a little confusing there.
Well, then,
I should add it.
I have to look at
So if you look at the first line, what
if your land is 1, 0, it would just be 18.
So B is 1, that's 0, everything else just comes. Given that
Well, I guess.
Okay, so thanks for the good question. I'll make sure to clarify like the notation if lambda is equal to, whoopsie. I'll make sure to clarify that, let's just say if lambda is equal to 0, look at first line. Okay. So, and I'll make sure to clarify that in next year's slides. So, in that case, everything drops off. So if lambda is equal to 0, all the other estimators go away. Basically, you have no weight on all of the advantage estimators that are 2 or more, and so it just becomes the first term, and the first term is the TD estimator. Yes?
When lambda is equal to 1, shouldn't the entire thing become 0?
If what?
If lambda is 1.
If lambda is 1, yeah. So if the lambda is 1, well, then you're summing from an infinite number of terms too. But yes, neither. Well, so this is this is true, so B is true. And the second one, we'll see on the next slide. I mean, it's a little weird to write down in this fractional infinite horizon because you can't ever do Monte Carlo returns with infinite horizon. So, but it's a good, you guys have good questions. I'll make sure to like clarify what happens in like sort of the h equals infinity was 1 and lambda equals 0 cases, just so that like the infinities are clear. But this is certainly false because this is not TD0, because we'd have a whole bunch of terms here and there'd be this weird weighting in that case. Okay, and then this, because then you sort of have to weigh how much is this term versus the infinity of the other, like the 0 versus the infinity of the other term. So I'll make sure to clarify that. D is also true because once this is a TD estimate, then we generally know TD estimates have higher bias and lower variance. Okay, so these are true. Now note in general, you would think therefore you want to put lambda somewhere in the middle because it will be balancing between bias and variance. But what they do in PPO is a little bit different, but it's related to this. So this is what the generalized advantage estimation is. You kind of do this like exponential weighting over lots of different advantage estimators, but without actually having to have separate copies in memory of all the advantage estimators. So that's why this is nice. So what we're going to do now is see what they actually did in PPO, which is instead of doing all of these, we're just going to do a finite number. So what they're going to do is a truncated version where they use this, but they only go up to a certain point. Okay, so they're not going to go up to forever. There's multiple benefits to this, including the fact that they're going to be in episodic domains. And what this means is that let's say your horizon is very long, but not infinity. So your horizon might be something like 2,000 steps for your mount car or something like that. You might pick t equal to be 200. And what that would mean is, so remember one of the benefits of temporal difference learning compared to Monte Carlo is that you can update your estimate after every step. The problem with the advantage estimator that is defined here is you still have to wait till the very end to update your estimate, estimator, because you need your advantage with near infinity, and then you're going to weigh all of them. So you don't actually want to do that in practice. So one thing that PPO proposes is to say, well, why don't we just do a truncated version? And that means every t steps, like big T steps, so let's say t is 200, every 200 time steps, you can compute this. You compute your new sort of weighted average estimate, like your advantage estimator, and then update. So you can think of sort of the big T here is determining how long you have to go before you can make an update. So that's what they do in PPO. They use this truncated generalized advantage estimation in order to get better estimators. Okay. Anybody have any questions about that before we move on to going back to this question of monotonic improvement? Okay, so now let's go on to another important feature of PPO, which is, it's really sort of in some ways going backwards, but I wanted to make sure to go through the algorithm for last time so that you guys could start working on implementation. But I think, and as in many papers, the theory is a little bit decoupled from what's actually done, but it sort of serves as motivation. So I think it's useful to go back to the bound that was proposed there that helped inspire their algorithm and think about what it actually implies about what happens when we do updates. Okay, so remember that, and as you're proving right now for homework 2, remember that what we do in, what they were thinking of doing in PPO was to say we want to be able to use our old data from a policy pi to estimate the performance of policy pi prime. But the problem is that in general that's going to induce a different state distribution. And so we played this approximation and said let's just ignore the difference in the state distributions. And that's great because now we can use our old data to estimate the value of our new policy, only our old data. Because we always know what the actual policy parameter is, but we don't actually have to gather new data from it. And we called this sort of L pi pi prime because pi prime is here, but everything else is being used by pi. And what was proven was that if your two policies have a close scale divergence in terms of the actual actions they take, then you get this bound on performance. Okay, so it said this approximation is not too bad. And in particular, we get this thing of sort of this monotonic improvement theory, saying that the value here, so I'll just write down that j of pi is equal to v of pi. Some people use j, some people use v. We mostly use v in the class. Okay, so that the value of your new policy pi prime minus the value of the old policy is greater than or equal to this term that we had on the previous slide. So this L term, this whole thing. Minus this sort of error that we get from the fact that we are approximating the state distribution by something that's not true. Okay, so we have this nice bound. And now what we're going to go through now is to show why, if we maximize with respect to the right-hand side, that we are guaranteed to improve over pi. That shouldn't necessarily, well, I guess I'll ask first. So who has seen this sort of majorize and maximize algorithm before? I wouldn't expect you to, but call me when I'm sorry. So this kind of goes back, I think we've seen ideas related to this in policy improvement from the very beginning. But this is different because we've got sort of these bound stuff. So what this is saying is this is a lower bound, right? Like this says that the difference between these two policies is at least as big as this term minus this term. But it shouldn't, and what we're actually going to propose to do is to say, all right, well, if we try to pick a pi prime that maximizes this lower bound, does that actually mean that we're going to be guaranteed to improve over pi? And it shouldn't necessarily be immediately obvious that that would be true, okay? But it's going to turn out that that's the case. So let's just go through the proof for that, which is pretty cool. All right, so we're going to prove that if you do this, if what you try to do is pick a policy, pi k plus 1, which is the argmax of this lower bound, that you will in fact get a new policy that's either at a local optima or is actually better than your previous policy. So that's the idea of what we're trying to do. Okay, so note a few things. Okay, so pi, so we're going to assume that we have some pi k, that's our previous policy, and that it was feasible. Okay, so like it's a well-defined policy, sums to 1, you know, it satisfies all of those constraints. Okay, so now let's just write it in terms of, okay, so now recall that, let's just do something a little silly, but it's going to be useful. Okay, so we're going to look at what L pi of pi k of pi k is. Okay, that's this term. All right, let's just see what that is if we just plug in, if we try to evaluate what that term, what that sort of expression is when we plug in the same policy as what we actually use to gather our data. All right, so remember that would just be equal to 1 over 1 minus gamma, expected value over S according to d pi k. Just writing down the definition of what L is. Okay, and this is going to be pi k of A given S divided by pi k of A given S times A of pi k. All right. Well, this is just 1, right? So this cancels. But the important thing to remember here is that the advantage function of a policy with respect to itself is 0. So if I take actions according to the current policy and compare what the value is to taking actions according to that current policy and then acting according to the current policy minus just first taking actions according to the current policy, that is, difference is 0. Okay, so that's I can just write that out too in case. Right, so just remember, like what we have here is we're going to have q pi k of S A minus v pi k of S, okay? But notice what we have here is that what are we taking, you know, what's the distribution we're taking these actions? It's exactly pi k. So q pi k, if you first follow, like I can just write that out just in case it's helpful. is, so this is like sum over A pi k of A given S, Q pi k of SA, which is just equal to V pi k. It's like if you start taking this action and you follow the policy, and then you follow the policy from all future time steps, versus if you just follow the policy from now till forever, that's exactly the same. So that means that this is 0. And that's good. That means that, like, because if we think back to what this looks like, that says that the difference between the value of the policy and the policy itself is 0. So this bound is tight if you are evaluating it with respect to itself. There's no difference between the value of the policy and the policy itself. Because the dk, oh, well, I'll say the next thing. So then, because also dkl of pi k to pi k is equal to 0. There is no KL, the KL divergence between a distribution and itself is 0. Okay. All right, so now let me just label these two. Let's call this term 1 and this term 2. Okay. So what we have here is we have that term 1 is 0 for pi k and term 2 is 0 for pi k. All right, so that means 1 minus 2 has to be at least as great as 0. Does anybody want to say why that is? I made an, that's not immediately obvious from these steps yet. You have to make one more step, and it has to do with the argmax. Let me see why that is. I want to share. Why is 1 minus 2 always have to be greater than or equal to 0? Given the argmax.
Because we know of a policy that's going to be 0.
Achieve 0 for the lower.
Exactly, yeah.
Exactly what we said, yeah. So pi k is an existence proof that there exists at least one policy for which the right-hand side is 0. We're taking an argmax over the whole policy space. That means the argmax has to have value at least 0, hopefully better than. And so that is exactly why. So because argmax is at least as good as pi k. So we're trying to maximize that. Okay, so what that means then is that, so remember all of this term here on the right-hand side was what we had here. Okay, so this whole, so we had j of pi k plus 1 minus j of pi k is greater than or equal to term 1 minus term 2, which we just showed is greater than or equal to 0. So what we just proved is that by maximizing with respect to our lower bound, we got a new policy that was at least as good as the old policy, which is really cool. So that means that using a lower bound on the gap between the performance of the policies is sufficient to allow us to make monotonic improvement. So that's super elegant. So now we could have something, if we actually did this, most policies do not do this, and we'll talk about that in a second, but if you actually did this, you would get monotonic improvement. And there's certainly like a number of domains where it'd be really cool to get monotonic improvement. So I think I've mentioned education before, but you could imagine healthcare as well. Like for a lot of cases, if you're doing stuff in the intensive care unit, et cetera, people might be kind of worried about doing random exploration or epsilon greedy. But if you could say we're only going to improve when we know that the new policy is at least as good as the old policy, that's likely to be a scenario that's much more palatable. Okay. All right, so I wrote this out a little bit more here, and one of the elegant things about this is that we can restrict ourselves to parameterized policies. This doesn't mean we have to have, completely, we can think about any sort of policy class, and as long as we initialize, so our initial policy is in that class, it could be a Gaussian, it could be a deep neural network, then you will, and then you keep doing argmax over your policy class, you'll get this monotonic improvement. So it's really nice. It's really elegant that you could do it in this case. But unfortunately, like many beautiful theory things, it has some limitations. So if you look at the actual, so C is a constant, and we haven't went through what a constant is in class, but you're welcome to look it up in the paper. When gamma is near 1, and what gamma near 1 means is that we care almost as much about long horizon rewards as we do about immediate rewards. When it is close to 1, gamma is pretty large. And so what that means is that in general, that second term can make you be very conservative. So why is that? Well, that means if C is really large, that means that if your new policy takes actions that are quite different than your old policy, you're going to have a really big penalty. So what that basically does is it shrinks your step size. It says, this is going to be a term that is weighed a lot, and unless you only make very small changes, you could get a big penalty. Essentially because you're saying, I'm really not sure. It might be that when I change my policy, I end up with very different state distributions, and I don't know whether the rewards would be there. So what that means is that in practice, if you actually try to use this equation directly, like just straight from the theory, the step sizes are too small. Now, when people say they're too small, that doesn't mean that there's anything wrong with them. It just means it's going to take way too long. It just means that people are impatient. But either impatient or, we're being very sample inefficient. So it means that this is reasonable. It will hold. You will get monotonic improvement. It's just going to take a really, really long time, and it's not going to be feasible for a lot of things, or it's not going to be practical. And so that is what sort of helped motivate why you might want to tune the KL penalty, which we saw last time, where you sort of increase or decrease how much you care about this penalty, or use a trust region, or use the clipping. And so that's why we see sort of a difference between what's formally guaranteed by if you were to just directly use this lower bound versus what's actually done in practice. But I think in terms of kind of the take-homes from this part on policy gradient and PPO is that it's really useful to know that you don't just have to take one gradient step. You can be much more data efficient. You can play this trick of pretending there's no change in the state state distribution in order to take several gradient steps. And that you can do that while still trying to maybe approximately get monotonic improvement. PPO does not guarantee monotonic improvement, but it can be pretty close, by thinking explicitly about these lower bounds and how much your performance might change and how much essentially your state distribution might change so that when you're not confident in these approximations. It also uses generalized advantage estimation, which can be helpful. And as I mentioned before, it's extremely popular. You can use it in many, many places, in part because also you don't need your reward function to be differentiable. So people have used it in lots of domains. Okay. Right? And the other thing that I think is just useful to remember when we think about policy gradients is that you can also use them with actor-critic methods. So you can have deep neural networks to approximate your value function and then use that for your advantage estimation and combine them. And so that's what most people do, is that they have some sort of critic, aka your value function estimate, and a policy. And these are only two, reinforce and PPO are of course not the only policy gradient algorithms, but they are the backbone to, with all this still used empirically a lot, and then also they're the backbone to many of the other ones. So if you read other papers, they'll be really useful baselines that you often see or that people are building on. All right, we're now going to go into imitation learning, but does anybody have any questions before we start there? Yeah.
On slide 22, just a general question, or I guess, sorry, the one before this. Yeah, so this, does that mean when the policy is more myopic and gamma is near 0, then your step size will be you'll be able to improve more to a greater extent?
Yeah, that's a great question. So you're like, is the converse good? So if gamma is near 0, is this practical? I don't actually know off the top of my head what C looks like for gamma equals 0, or not 0, but near 0. So I don't think anybody uses this in practice. I think they always use the clipping or the KL trust regions. So my guess is that it's still not practical. Oftentimes the C constants will often be a function of Vmax, your maximum value, often scaled by 1 over 1 minus gamma. So it can really be quite enormous in many cases. So it might be that here it was particularly, they might be interesting cases where your horizon's pretty large or where I think one thing here too is that if we're in the episodic case, there's not really a good reason to think that the discount factor shouldn't be near 1, because you probably actually do just care about all the rewards. So they're probably mostly interested in domains where they didn't think it was reasonable. But yeah, it's a good question. All right, let's talk about imitation learning. Okay, so as we've said before, in general in computer science, we like to try to reduce things if we can. We like to reduce them to other problems that we know how to solve. And so imitation learning is going to be our attempt to try to do that, at least in certain ways, for all of reinforcement learning. Okay, and some of these slides come from some of my colleagues at Berkeley and at CMU. So in general, we're going to now be thinking about the case where we're not going to be gathering data online. So we saw in PPO that we tried to reuse our data a little bit more to take bigger steps. But one thing you might wonder is, well, why do I need any more data at all? Couldn't I just gather some data and then just use that? And maybe I don't need to gather any new online data. And we'll see more ideas about that shortly. But one case where you might think that would be reasonable is, what if you have great demonstrations? So, you have instances of doctors making really good decisions in the intensive care unit, or you have people flying planes, or you have people driving cars. Why couldn't we just use those examples to directly learn decision policies? Okay. And so the hope would be there is, like, if we just have those recordings, anytime someone's driving like a Tesla, or someone's driving an airplane, could we just get those sort of state action pairs and tuples and use that information to try to learn a policy directly? Now, one thing you could do instead is to say, like, well, you'd have a human in the loop, but that's going to be pretty expensive. And so the hope would be that instead we could just use the demonstrations people are already doing, and that might be much more reasonable too in terms of people's time. Okay. So one thing in this case would be, all right, now maybe we're going to try to just look directly at demonstrations, and that means we're not going to need to have anybody to label things. This is an example from sort of trying to understand what the reward function might be for driving. So I guess I just would say, in addition to the fact that we often have data about people doing these sorts of complex tasks that we'd like to imitate, it also might be in those tasks that it's really hard for someone to write down a reward function. Like, maybe in this sorts of setting, like, you want to avoid the water unless it's really, really steep or really gravelly, in which case maybe your truck or train can go into the water. Or maybe, like, in general, you want to avoid trees, but again, if it's really slippy and muddy, it's actually better. And so it might just be that it's really hard for people to write down a reward function in this case, but they could drive it and sort of indicate that implicit reward function. And so again, that might be easier to gather. This comes up in a lot of different cases, and people have thought about it certainly a lot for kind of manipulating heavy machinery or manipulating cars or things like that. But for things like driving and parking and stuff, those are a lot of cases where people provide those sorts of demonstrations where it might be hard to specify that reward function. So the idea from learning from demonstrations is that you're going to get a number of expert demonstrations. So experts will demonstrate things, whether flying a helicopter or manipulating, something with a robotic arm or stuff, like through teleoperation. Dorsa group does a lot of this. And it will give you a sequence of states and actions, not rewards. So you just are going to have, like, trajectories of state, action, S prime. Okay, so we're not going to have any rewards anymore. Everything's just going to be implicit in this case. And now we're going to assume that it's easier for people to do this. So they're just going to hopefully be able to provide these demonstrations, or they maybe already have. So what's the setup for the rest of today? The setup is that we still have a state space and an action space. We're going to assume there's some transition model. And there's a reward function, but we don't know it. So there might be a reward function, but we don't know it. So there's nothing explicit here. There's no explicit rewards. And that we have these set of demonstrations. In behavior cloning, what we're going to do is just reduce this to supervised learning and try to learn a mapping from states to actions. We're just going to try to clone the behavior. And then we're going to also see some about, can we actually recover the reward function that people might be using to generate their behavior? And then if we have that, can we actually try to get a new good decision policy? Right? But the first one is just kind of to try to directly learn a policy. This is called behavior cloning. And essentially, once you decide to do this, this is just off-the-shelf supervised learning. So now you treat it as you have a sequence of states and actions from your expert trajectories, and you can use whatever tools in supervised learning you want. So just anything can be done there. It's just to reduce, it's strictly now made it into a supervised learning problem. And there were some really early successes, so like Alvin from a very long time ago, and then in 1992 learning to fly in a flight simulator, really early on in sort of the history of reinforcement learning, or like kind of the modern history of reinforcement learning, people thought like, could we just reduce this problem? And we'll see in a second what's one of the challenges that comes up when we do this, but it certainly can be really helpful. So it's kind of fun to look at Alvin. This was, late 80s. So, but I think that's must have been kind of amazing. They were already thinking about cars then. They're already thinking about not so deep neural networks, but they were thinking about neural networks. I think this came out of CMU, if I remember right. And they had this like tiny, 30 by 32 video input. And they used this rangefinder. And so they were trying to, use not so deep neural networks to do behavior cloning for driving in the late 80s, which is pretty awesome. So it can be done pretty well. In reality, this is something that still people try a lot. It's a really good baseline to try if you have good data. And I'll talk about some of the challenges with doing behavior cloning. But I think one thing now is like if you have a lot of data, like a lot of demonstrations, like imagine you have all the data from all the pilots, like you have their actual, what they're doing, all of the different sort of input actions they're doing, and you have that from, I don't know, all of United or something like that. So if you have an enormous amount of data and you have a pretty sophisticated supervised learning technique, it can work really well. Particularly if you use behavior cloning with an RNN or something that takes track of the history. So while what I wrote here involved just states and then like the last state, like a Markov assumption, like the state and the action, you don't have to do that, right? You could also say, I could have my state, action, state, and then go from there to A1, or like state, action, state, action, state. So you, in general, could use something that it was like a recurrent neural network or anything that keeps track of long-term histories. It does not have to be a Markov representation, and that often can work very well. Again, it depends a lot on your domain. I think that there's a nice paper a few years ago in Curl, which is one of the robotics learning conferences, where they looked at sort of what were some of the important factors when you're doing offline learning and for robot applications. So it doesn't always work well, but it can work really well, particularly if you use history.
In what domains would having history help?
Because imagine if you're thinking flying or driving, really what matters is just the current moment. So when is actually helpful?
I actually would debate that. So I think it's a great question. I think maybe it partly depends on how you're thinking of the state space, but I think if your state, let's say I'm driving, if my state is just my immediate position, that's probably not enough. I probably need at least my last few to get to velocity and acceleration. So you might already be thinking, oh, in my state I already have those. If that's the case, if your state already incorporates something about the first or second order derivatives, that's probably okay in some cases. But in other cases, if it's just your immediate, then immediate sensors, then you want the longer history to capture that. And same for planes and stuff. Yeah, it's a good question. So this is always just a really good thing to try. It's a really natural baseline. It's generally really easy to do. People often report it in offline RL. It's extensively used. It does not always work. Let's see why it might not work. And I think one of the themes that you're seeing now with the policy gradient work now is this challenge of what are the states you reach and how, when you use different policies, you're going to end up in different states. In general, that's sort of the definition. If your policies don't ever reach any different states and they never take different actions, they're the same policy. They generate the same trajectories. So Dagger was a paper, 2008, I'm trying to remember. It came out in the first decade of the 2000s to try to address some of the challenges with behavior cloning. Okay, and I think what they were noticing is this challenge of if you do behavior cloning, sometimes things go badly. And essentially that's because the decisions that you make over time can have sort of cascading effects. So let's see what that might look like. So if you do something like supervised learning, and this is what we do when we would be reducing our problem to like imitation, like in behavior cloning, we just reduce it to supervised learning. In general, we assume that our pairs, our data points, like our XY pairs in supervised learning are IID. So they're independent and identically distributed, and they're ignoring temporal structure because they just assume they're totally independent. But in our case, they're absolutely related. In fact, if you assume a Markov structure, then what happens is you have S0, A0, S1, and so whatever you did here exactly helps determine what is the next state you do. So the states are definitely not independent, all of your different time points. So one of the challenges with that is that if you have independent in time errors, and generally that's not too bad. And that's what most of our supervised learning guarantees are for, is that you assume your data is all IID, and then you can think about how much sort of error in your estimates, what sort of error you get. So in general, if you have an error at time t with probability less than or equal to epsilon, and you have t decisions, so let's assume we have t decisions, then your expected number of total errors, if all of your decisions are independent, is just epsilon times t. Bless you. Because they're all IID. Okay, and that's not too terrible. But that's not what we normally have in, oh, I see what happened there. Okay, let's think about something else. I'll add a different picture later. Let's think of a racetrack. Okay. All right, so in this case, you have a racetrack, and your car is driving. Except for your supervised learning thing isn't perfect, and so it makes a small error. So what you actually do, you should maybe you actually should have went this way, but you went to the black part. Okay, and now you again make a little bit of an error, and now you're off the track. And now this is really tricky because you may have almost no data in the part of, because your humans never decided to drive off the track. And so now you're in part of the region where you have very little data, very little coverage, and you're even more likely to make mistakes. And so what you can see in this case is that if you make small mistakes early on, those can compound and get you into parts of the state space where you have even less coverage, and you generally have even less accuracy. And so in general, you can actually do much worse. And this is because you have a data distribution mismatch. If the policy that you compute gives you a different distribution between train and test, then you don't necessarily have the same guarantees. Okay, and we're going to get a different distribution here because the policy we were using to gather the data is not exactly the same as the policy you get now. And we saw that in PPO too, that when the policy changed, we're going to get to different states and actions. What's causing our policy to change here is the fact that we can't perfectly imitate the expert. Okay, so let's just see what that looks like. So in this case, we had, in our training set, we had pi star, which we assumed to be our expert, and we were generating states from pi star. In our test set, we have learned a policy by trying to match the state action pairs we saw in our training set, and we're getting a different distribution of states. Okay. So in general, this is going to be different, and we're going to get worse errors in this case. Sorry about let's see what happened in this case. So I'll just draw it. Okay. So what can happen in this case is, let's say this is the error you make now, and then you can make another error, and it keeps compounding. So if you make an error at time step t with probability e, essentially what can happen there is that you may then make errors on the remaining time steps. So it may sort of cause you to get into parts of the state action space for which you make lots of errors. And then you sort of incur lots of regret or costs through the end. And so in general, and I'm not going to step through all of the proof today, the error can actually compound instead of linearly with the number of time steps, it can compound quadratically, which means that essentially your performance is much worse than supervised learning would predict. Supervised learning said, oh, I've got an epsilon optimal or epsilon accurate policy, great. And what this says is because all of those decisions are being made across an entire trajectory, you can actually end up with epsilon times t squared errors instead of epsilon times t. Okay. So this is what motivated Dagger. Dagger said, okay, what's the problem? The problem that's happening here that we'd like to address is Whenever we make mistakes, we go into a different part of the state space. Once we're there, we maybe have very little guarantees that we're going to do anything reasonable. So essentially what we want to try to do is kind of figure out how we might correct or adjust to those states that we reach that weren't in our original training set. So the idea in this case is that this is going to be an iterative approach. So you get a data set where you take a current policy and you execute it in the environment. So it's like, you drive your race car around a track. And hopefully, it's similar to what the expert would have done, but probably not perfect. And then what you do is you go to your expert and you say, okay, this is what I did when I went around that track. What should I have done? They're like a coach. And so then what the coach does, or the expert, is they say, in each of those states, this is what you should have done. Okay, so it would say, if you went like this, and then you did this and did all these other crazy things after that, it would have said, okay, no, first of all, here you should have gone here. And then once you reached here, you should have went down to try to get back onto the road. So essentially what you're having a human do is you're having them label at every time point, at every state in that trajectory, what they would have done. And when you do that, that gives you a new set of data to learn from. So it's like, your expert pilot gives you feedback on every place you made a mistake when you just did your last flight run. And then you integrate that. You're like, oh, okay, when I'm feeling this form of lift, next time I got to do this. So it gives you a whole bunch more data. And then we aggregate that data. That's why it's called Dagger. So we're aggregating the data sets of the old data we had and the new data that we just got from our expert. We then do behavior cloning again on our new data set, which now includes more of the states in the environment. And then we repeat. And I think part of the motivation for this, and this is why I said behavior cloning can work really well when you have enough data, is that the problem that's happening here is that we're assuming we don't kind of have full coverage over the whole domain of what the expert would do at any place inside of the, say, race car track. And what this is allowing us to do is to better figure out over the whole space what the expert would do and make better decisions and correct in case we end up in those. So in Dagger, we do this over and over and over again, and there's some nice theoretical guarantees of what you'll converge to when you do this. And what they did is to show this for things like driving in like a simulated domain, like a Mario Kart or a video game, and show that they could learn quickly how to sort of get a very good policy that didn't suffer from these kind of compounding errors. Can anybody think of what a limitation might be of doing this over behavior cloning? Yeah. Exactly. It's super expensive. Yeah. So you have to, basically, it's like you have to have that coach or your teacher or your expert with you the whole learning. So the nice thing about behavior cloning is you get data once, the data might already be available, and then you can just learn from it. Here you have to have constant supervision. Now in some cases that might be reasonable, but in most settings that's going to be really infeasible. So this is very human in the loop. Human has to supervise. And so I think for those reasons, that's one of the reasons that, in robotics and some other areas, people certainly have built a lot on Dagger, but I don't think it's as popular as behavior cloning, because it really does require a lot more work of the human. All right, so the second thing you might want to do is learn a reward. So you might say, all right, I'd like to actually figure out what the reward is. You might want this for several reasons. You might want to learn the reward because you want to understand something about human decision making. Like you might say, all right, I want to understand how surgeons are making trade-offs when they're dealing with really complicated situations of like, how do I trade off time or risk or things like that? And maybe it's really hard, or just, their time is really valuable to ask them lots of questions, but you really would like to understand kind of that preference structure. So that's one goal. And another is that you might want to use that then to learn a policy. You might say, like, if I can extract that from the data, then I can learn a policy from that. And you'll see that in homework 3, because we're going to be doing RLHF as part of that. So we're going to try to learn from preferences. So there's lots of reasons you might want to be able to learn a reward function. So in this case, we're going to be in a similar setting. We're going to still have a state space, an action space, and a transition model. Still no reward function. Still going to have some expert demonstrations. And what we want to do is infer the reward function the expert was using implicitly to make their decisions. And what we're going to assume for now is that the teacher's policy is optimal. So like, or you can call it expert. The teacher or the expert's policy is optimal. So let's think about what we can infer from that. So if you see someone's demonstrations and you know that they're optimal, so teacher, I'll use teacher equals to expert for this thing. If you see these and you know it's optimal, is there a single unique R that makes the teacher's policy optimal? Are there many? Does it depend on the markup decision process? You're not sure. And remember, we know that the actual policy is optimal. And if you think there are many, I'd like you to give me an example, simple one, which would make things optimal. I mean, not in the thing, but I'll ask in a second. All right, why don't we just do a quick check and talk to a neighbor and see what you think.
Yes, I am. I don't really understand how do we represent that as the whole so you're talking I didn't know.
Wouldn't it be the same yeah.
Okay, good. So almost everybody said the answer is B, which is true. There is many. Does anybody want to tell me kind of a silly one that any policy is optimal under? Yeah.
Like 2 are like just scaled by a constant factor.
Yeah, that's great. And I was hearing that too over there. So if you take a reward function and you multiply it by a positive constant, like then that can't change the policy. 0 works too. So you can just use 0 and any policy is optimal if you never get reward. So I bring this up, not to trivialize it, but just to highlight that this is a huge identifiability problem. So there is not a single R. Even if you know that the demonstrations are expert, there's not a single reward function that's compatible with them. And so that's a problem, and that's something to keep in mind when we start getting into RLHF and DPO shortly, that this is either you need to be making other sorts of assumptions to constrain your reward function, or in general, we're going to have to make additional choices or constraints, because otherwise this is a not identifiable problem. Great. So one thing some people do to try to think about how we might do this is to think about, I think I know what happened. I was editing 2 sets of slides, and I think the other one is now well updated, but this one was not, unfortunately. In any case, we talked briefly about value function approximation through deep Q-learning. Deep Q-learning naturally implies that we would use a deep neural network, but you could use a linear value function, just like, a very shallow network. The idea here, and this is all that this work predated deep Q-learning, is to think about generally where your reward is linear over the features. So your reward of S, so here we're just doing reward with respect to states, is W. W is just going to be a feature vector. W is just going to be a vector, X of S. And X of S here is just a feature representation. So this is just features are X of S. So that, for example, could be like if I'm a robot, if this is my current location, what's the distance to that wall, what's the distance to that wall, and this wall. That would be a set of features. And then I could have a weighted combination of those to give me the reward of me standing here. And the goal is to identify the weight vector W given a set of demonstrations. Okay. So in that case, you can also express the resulting value function for a policy as a combination of these weighted features. Okay. And let me just write it out. So let me just write it out, sort of, particularly because we didn't do it in class very much. I'm going to write out sort of what that looks like. So it's the states we reach under this policy, this time steps t equals 0 to infinity, gamma t of our weight vector that's unknown, times our feature representation for that time step, given we start in S0. But note here that W is always the same, so we can just take this out. Okay. So we have WT, the expected value S to the pi. And this should start to look somewhat familiar because it's going to look like these weird discounted features that we've seen sort of before. So we can also call this WT mu of pi, where this is the state distribution under discounted state distribution under pi. Okay. We've seen this before where we go sort of back and forth between thinking of there being time steps and thinking of us as sort of saying, well, over all time, how much time do we spend in each of the different states? So in particular here, I've defined mu to just be the discounted weighted frequency of state features starting in a particular state. So why have I done this? Well, I've done this to say we can relate what the value is to just a linear combination under this linear reward function, a linear combination of my weight feature, which I don't know, times my feature distribution. Okay, and that's good because I have access to features. I have access to trajectories that were demonstrated by my experts, and I can use that to extract the features of those states and compute something like mu. So, but we don't know what W is yet, so let's think of what we could do. So the goal here is that we want to identify the weight vector W given a set of demonstrations. We've just seen that we can rewrite the value of a policy pi, if these rewards are linear, as WT mu of pi, where it's the discounted state frequency. All right, so what we know is that V star for the optimal policy is greater than or equal to V pi for any other policy. And that means that W pi of mu pi star has to be greater than or equal to W pi of mu pi for all pi, where this is observed. Sort of experts. So what it means is that if I pick any other policy and I generate what are the state features you'd get under running that policy in the world, that distribution of features has to have lower reward than the features I've actually observed in my data, because I've assumed my expert is optimal. So my experts demonstrated things, it's optimal. And when they demonstrated things, like let's say they're controlling a robot and the robot spends all this time over in this part of the room. And if they spend time over this part of the room, then all my features are going to come from over here. And that means that any other policy that I use, its features have to have a lower weight if they don't match what the features are of the expert. Okay? Regardless of what W is, right? Because this has to hold. Okay? So this is, for the W that we pick, this has to be true. So we can rewrite that as saying that the value of V star has to be greater than V, which means that the value under we can just write it down in terms of this and the resulting frequencies. So therefore, the expert's demonstrations are from the optimal policy to identify W. It's sufficient to find a W star such that this holds. So we know this has to be true under the true expert, that under the true W, it has to be that features we get under the expert policy have to have a higher reward than the features we get under any other policy. So this gives us a constraint that says when we are searching for what W is, because remember W determines our reward function, this has to hold. Okay, this is a constraint. And then what we can do is, so it's sufficient to say, well, what would be one thing we could do to be optimal if we want to get to a policy? Well, we just need to match the features of the expert. So we need a policy that induces the same distribution of states as the expert. So in general, if you have a policy such that the features you generate under that policy are really close to the features you get under pi star, then for all W, with W infinity less than or equal to 1, this is using Hölder's inequality, you're guaranteed that the reward of this policy is very close to the reward of the optimal policy, or your expert policy. And all of this is just to say you can reduce the problem of sort of reward learning and policy learning in this case to feature matching. That's kind of the high-level idea, is to say, in the case where you don't observe the reward directly, but you have access to optimal demonstrations by an expert, all you need to do is to find a policy and a reward function that allows you to match those features, because those are the features that we know have high reward. All right. Now, as we've already talked about, there is still an infinite number of reward functions with the same optimal policy. So even when we think about this mapping to features, it doesn't solve the issue we just identified. And there are many stochastic policies that can match the feature counts. So I haven't told you anything yet to solve that big problem. I've just told you sort of another way to think about it. And so there's this question of like, how do we pick among all these different options? So there's a number of different ways to do this. Some of the largest and most influential ideas are these two: maximum entropy inverse reinforcement learning and Gale. And what we'll do next time is to talk about maximum entropy inverse reinforcement learning, which has been very, very influential. So this is in 2008. So we'll pick up on that on Wednesday. Thanks.